with 2.1, 2.1, 2.1, we need to do the following. We need to find the equation. We need to find the equation of the tangent. Tangent 2. Equation of the tangent 2. So we need to find the equation of the tangent 2. So I want to look into one that is found in a book. Which book is this? J.V. John. J.V. John. And 5. So finding the equation of the tangent, we are given the following function equation: x squared plus xy plus y squared. It is equals to 7. So we need to find the equation of the tangent to this equation of function. At -2, it is to 3. So -2 is to 3. We need to find that equation. I hope that one is visible. So try to find the equation of the tangent. So first of all, we know what is a tangent. It's a tangent. We're talking about let's say a line passing through either one point, and it's a straight line, isn't it? So it's a straight line. So, but when we need to find the equation of a straight line, y equals to mx plus c, there's a few things that we need. We have a point, we can manage to find at least the constant, but we have an unknown in terms of m, which means we need to deduce our gradient. Where will we get a gradient? So we know that if we can change this function in terms of x, so we need to note that, when we derivate the function, we know that the function at any point, the derivative of the function gives us a gradient to over the x is equals to m. So which means we can manage to find a gradient from this equation from the derivative of this function when we are given a point. We can substitute from the derivative. So we need to work it out by changing the function in terms of x. So we start the derivative of x squared. It's going to be equals to 2x, isn't it? Then here we have a product of functions. The derivative of x is 1 multiplied by y. In the second term, it's plus derivative of y now. Derivative of y, it is dy over dx. So we use product rule in the second term. Derivative of x is 1 multiplied by y plus the derivative of y times x. The third term, when we derivate, we're going to get 2y. Changing y again in terms of x, dy over dx. Isn't it? So 2y, change y in terms of x, dy over dx. Therefore, it is equals to derivative of a constant, derivative of 7. It is 0. Derivative of 7 is 0 in terms of x. Then from there, we need to get our what is it? The equation of the gradient to say, or the slope. So we take out the common factor between the two terms here of dy over dx. We'll have x plus 2y all multiplied by 2 dy over dx. Therefore, everything we take it to the other side that we didn't take out the common factor from, which is negative 2x minus y. So negative 2x minus y. Then from there, we can state that, dy over dx is equals to minus 2x minus y divided by x plus 2, 1. So minus 2x minus y, all divided by x plus 2, 1. Now the second part, we need to state that, we know that dy over dx, the derivative of that function can help us to get the gradient of the slope at any point of this function. So m is equals to that. X plus 2y. So we can specify that at x is equals to negative 2, what is the gradient? At that point of the tangent, if we could plot that function, I think, allow me, will it work fast? Let me check the graphings. If we can graph the following function. So if we can go and check Desmos graphing and just that this function is consisting of, let's say it's x squared, right? It's x squared plus xy plus y squared, which is equals to 7. So that's our function, right? So that is the function. So we're looking for the gradient at x equals to negative 2. At negative 2 here, so I want to see at what point of y, or at point y is 3. Ne? So 2, negative 2. Let me see, where's 3? Maybe 3 is somewhere here. What's the point there? Yeah, it might be somewhere here. So one looking for the equation of that line which passes through that point then. Through that point. So let's just do a quick we get the gradient so we can get the equation and we'll see how it looks like. So x equals to minus 2. Therefore, what is the slope? So we substitute. In fact, maybe even at y, can we even have y? Y is equals to 3. So we need to get. So we have 2 into negative 2 minus into 3, all divided by x is negative 2, right? Negative 2. Therefore, plus 2 into 3. In fraction form, we have it in fractions. So it's 1 over 4. Just leave it as 1 over 4. Or 0.5. 25. We can leave it as 0.25. That is the slope. Then we're done. Remember, we have to find the equation of the line, of the tangent. So, normally I will advise, maybe if, let's say, you are given a gradient and a point, you can use this equation y minus y1, which is equals to m into x minus x1. So normally in previous level of N4, N3, could do the geometry of coordinates. Or you can use the one that we specified here and substitute and get C and take everything back to the original function. So while we're given it is 3, y1, gradient we just calculated is 4. Then in terms of the function x, therefore minus 2, so which is going to be plus 2. Let's just find the equation at once. 1 over 4x n plus 2. If we're going to take times that is 1 over 2. Take 3 to the other side is adding. So 1 over 2 plus 3. 6, 7 over 2, right? So it's plus. I think it's 7 over 2. So because this is plus 2 times 1 over 4, it is 1 over 2. Taking 3 to the other side, and it's going to be positive. Add 6, then we have 7 over 2. So this is the equation of the line for the tangent we're looking for. That is the equation of the tangent we're looking for. Mhm. So you'll correct it if it's incorrect there. But I want to quickly and plot the function. So the same graph y is equals to 2. 1 over 4, then x plus 7 over 2. So you see that tangent we're looking for. So it's passing through this point. So this is the exact function. But if you got it incorrect, it will be cutting or bisecting there. So yeah, this is the function. We do this. It's the function that we have. Yeah, so that's what we have. I wanted to open this and take it. I hope it's clear. I just wanted to show the graph how it looks like. How it looks like. Let's see if I can paste here. Oh, I must drag it. So that is the function there. Okay, but I hope all is clear. So that's how we apply implicit differentiation. That's how we apply implicit differentiation to even in applications to find the equations of a tangent or to derivate and get the equation of the gradient. The equation of the gradient. The equation of the gradient. What happened here?